Okay, so for 11-1, and this section today starts off our new section. So we have a new set of days for our calendar. And in case you hadn't heard, which I'm sure all of you heard so far, we are staying virtual like this for the rest of the year. So the next section, section 11, will go all the way through the next 4 weeks. Our next test won't be until May 15th. So we have quite a bit of material in this section. The last couple things that I have listed for this section, though, I'm telling you now, will not be on the test. So pretty much everything that's in what's considered our textbook will be covered on the test. The couple additional sections at the end that include density and scale factor will not. However, there will still be lateral area and surface area. So anything dealing with three-dimensional solids, the main basic properties that we're going to start going over today, anything to do with volume and anything to do with lateral area or surface area, those are going to be the things that are on the next test. The last couple things there, again, there's some stuff on density. So let's do this. I'm going to go ahead and circle again. This will be on the test. 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 But then starting with this day, these last two topics will not be on that test. So again, I'm going to go over those because I think they're important. They're also part of the curriculum. But some of the classes are in different places than we are. So like the other geometry honors classes a little bit behind us. So we're going to leave those couple topics off the test so that, again, everybody's getting a fair assessment and everybody's being graded the same way. So again, the ones that I circled are the ones that you're going to see on that next test. Just like the last one, I will have it open from Thursday through Sunday. So again, you'll have a few days that you can log on and test. So before we actually get into the material from the book, there's quite a few lessons, or I should say definitions, that go into the section that are expected to be known as prior knowledge. So in sixth grade math, you tend to do a little bit of geometry with shapes and solids. So again, a lot of these definitions probably look familiar, but might not be things you remember. Now, if you want to copy these down in notes, you can, or if you just want to listen as I go back through some of these, that's fine too. I put the main definition here and I put a diagram for each one. But again, a prism, it's a solid, it's made up of only polygons. You have two bases, which are going to be, and I'm not reading off the description that's there, that's the definition from the book. You have two faces that would be your bases. So there's two bases. They can be any type of polygon, and all the other faces that connect them have to be some type of rectangle or parallelogram. For a pyramid, you only have one base, you have a vertex at the top, all the other sides besides the base have to be triangles. But again, the base can be anything else. And you name those two shapes, the prism and the pyramid, based off of whatever the base is. So on the diagrams I have showing there, you have the two prisms, you have a pentagonal prism and a rectangular prism. For the pyramid, you have a square pyramid. For a cylinder, the cylinder, you have, again, a set of all points in space given distance, which is the radius from a line known as the axis. So if you drew a line right down the middle of that shape connecting the two centers of the circle, so I'm going to draw that right here. So, and if you imagine being able to see through this shape, so there's a circle on the back end, there's a center there. The line that connects them would be the axis. So every point equal distance from that axis is going to be the points that make up a cylinder. A cone. A cone is similar to a cylinder. It has a round circular bottom, and it too has an axis that extends from the vertex down to the base. Now, the cylinder is closely related to the prism because, again, you have two bases. The cone is closely related to the pyramid because you have one base and a vertex. You'll see a lot of similarities when we get into the formulas for those shapes. Sphere, again, a sphere is basically a ball. Its definition looks almost exactly the same as a circle's definition. The only difference between a circle and a sphere is that a sphere is a three-dimensional shape, where a circle is a two-dimensional shape. Other than that, the definitions are pretty much the same. And then a hemisphere just is half of a sphere, just like a semicircle is half of a circle. So again, those are some basic definitions. Other things that you should know: name of polyhedrons based on the number of sides. So when we look at polyhedrons, you can always name it based on the number of sides, just like we had polygons can be named with the number of sides. You'll notice most of the names here have the same prefixes as before. So the only one that's really different is four sides. Four sides is a tetrahedron. It uses a different prefix. Again, I forget one. I think one's Greek and one's Latin. And for a triangle, we use one of the prefixes. And same thing for a quadrilateral, we use one of the prefixes. For all the other shapes, for our polygons, we used the opposite type of prefix. Now, for our polyhedrons, same type of thing. Four sides, different prefix than what we had used before, because before we used quadra for four. Now it's tetra. So again, tetra means four. So we have tetrahedron, pentahedron, hexahedron, heptahedron, octahedron, nonahedron, decahedron, undecahedron, dodecahedron, and then I put 20 on there as well, just because if we get to the point where we talk about Platonic solids, which I'm not sure if we're going to do this year, we do talk a little bit about our 20-sided figure as well. So I threw that one on there. But again, those are names based on the number of sides or number of faces. So again, just things to keep in mind. Some other definitions that, again, you've probably heard in previous classes. A polyhedron is a three-dimensional figure consisting of polygons that are joined along the edges. So again, polyhedron, very similar to polygon. The only difference is, again, we're talking about a three-dimensional figure now. A net is a two-dimensional representation of a three-dimensional figure. So we'll look at nets as we go along. I'll have some shapes that I also show you guys that deal with nets. Faces are the polygons that make up the three-dimensional figure. Edges, they're the intersection of any two faces. A vertex is a point at the intersection of three or more faces. Now, a couple things to keep in mind here. You'll notice faces, it says polygons are there. An edge, something to keep in mind there, an edge will always be in the shape of a line segment. So I'm just going to jot that down here. Whereas a vertex is always a point. We're going to talk a lot about faces, edges, and vertices in this section. So again, these are going to be the three main things. Whoops. Let's try that again. Those are going to be the three main things that we talk about in this section. So oblique prism, there's two different types of prisms. Oblique prism, and really you can do this for any one of the shapes. An oblique prism basically looks like a slanted figure. A right prism is straight up and down. So oblique prisms, sides are going to be not perpendicular to the bases, whereas a right prism is perpendicular to the bases. All right. Okay, that does it for the basic definitions that you should be familiar with. This is where our book picks up 11-1. So now, this section in our book is talking about three-dimensional figures and cross sections. So first, we're looking at a couple different figures. And this first question says, how many faces, vertices, edges does each prism contain? Do you notice any patterns? So on these shapes, you'll see that we have, the first one is what we call a triangular prism. Because again, it has triangles as the bases, and the bases do not have to be the top and bottom. So this is a triangular prism. In this case, the bases for any prism are going to be the two sides that are in parallel planes to one another. So again, This is a triangular prism because the two triangles would be acting as our bases. Now, if we're counting these things, number of faces, well, we have 2 triangles and 3 rectangles. So we have a total of 5 faces. Then you have number of vertices. Well, the vertices are all the points. So if you count all the points, there's 3 points on one of the bases, right? If we look at it, there's a point here, 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 and here. So there's a total of 6 vertices. Then you have edges. Well, edges, there's 3 edges along each one of the bases. So those. But then you also have these that are connecting the bases. Those are called lateral edges. So there's a total of 9 edges. Now, there's a pattern to this. So if we keep looking at all these values, something happens with all of them. If you look at the next one, we have the rectangular prism. Well, in the rectangular prism, you have, again, counting all the faces, you have 2 faces at the top and bottom. You have 4 faces on the sides. So you have a total of 6 faces. For the vertices, 4 on top, 4 on bottom, total of 8 vertices. Edges, 4 on top, 4 on bottom, 4 going all around the sides for the lateral edges. So you have a total of 12 edges. So again, we can fill in the rest of this chart. And now looking at those, there's a pattern. So if you look at the numbers, does anybody see the pattern right now? Or if you're looking ahead in your textbook, does anybody see a pattern? Yeah, okay, I have some people saying yes, you see a pattern. Anybody know what the pattern is? So, all right, so we do recognize, some of you guys are recognizing patterns within the columns, yeah, but there is a pattern within each row comparing the number of faces, vertices, and edges. And Alex texted me the correct pattern here. If we add 5 and 6, we would get a total of 11. Well, 9 plus 2 is 11. On the next line, 6 plus 8 is going to give us 14. 12 plus 2 would be 14. So the pattern that we actually have here is if you take the number of faces plus the number of vertices, it'll equal the number of edges plus 2. So there are a lot of other patterns here as well. And quite a few of you gave me a bunch of other patterns there in chat. So thank you for recognizing a lot of those other patterns that are there. But the one that they are specifically wanting for this chapter is focusing on something that we call Euler's formula. So yes, it looks like it would be pronounced Euler, but again, it is Euler. It's not an American name. So Euler's formula is F plus V equals E plus 2. Most common mistake on here is people forget to add the 2. So a lot of times people will say F plus V equals E. Just make sure that you always add the 2 on that side. So you're adding 2 with the number of edges. So F plus V equals E plus 2. Now, there's going to be a lot of formulas in this section, so you may want to create a separate sheet of paper that lists all the formulas that we're going to have in this section. Most of the other formulas that we're going to be doing, we're still going to use the area formulas from the previous chapter. So again, we'll take a look back at some of those area formulas. And then we're going to be having formulas for volume, surface area, and lateral area. So come the next test, it'd be very helpful if you put all the formulas in one place. Now, for this next example here, so they want us to actually use Euler's formula. So we have our figure here. It says that we want to gain a piece that has 20 faces, 30 edges. How many vertices does the piece have? Well, if it has 20 faces and 30 edges, we should be able to figure out how many vertices it has by using our formula, Euler's formula. So we're going to plug it in. So again, it's F plus V equals E plus 2. Well, we know the number of faces. We're looking for the number of vertices, and we know the number of edges is 30. So now we have 12 plus V, can't do anything on that side. On the other side, 30 plus 2, that's 32. So we still have 12 plus V over here. Subtract off 12. So the number of vertices would have to be 20 for this type of figure. And this works for any type of polyhedron. So it works for prisms, it works for cones, it works for any other irregular looking polyhedron that we could make up. Doesn't have to be a regular. So same way that we had the word regular to define a polygon when we had all sides were the same length and all angles were the same, you can also have regular polyhedrons. But again, doesn't have to be a regular polyhedron, doesn't have to be any specific type of polyhedron, doesn't have to be a prism, doesn't have to be a cone, sorry, not cone, pyramid. Again, any type of polyhedron, this formula applies. So the next question is, can a polyhedron have 4 faces, 5 vertices, and 8 edges? So is that possible? Well, the way that we tell is plug it into the formula. So if we take that and plug it in, and we have 4 faces, 5 edges, sorry, 5 vertices, and 8 edges. 4 plus 5 is 9. 8 plus 2 is 10. Those aren't equal, so no. Again, since it doesn't work in Euler's formula, it cannot happen. Thank you. A few of you guys were answering the questions as we went along. Thank you to all those that are participating in the chat. Okay, on the next one. So now we're looking at cross sections, and our book kind of assumes that you remember what a cross section is from a previous math class, but I went ahead and put the study tip over here off to the side that's in our book as well. So a cross section is the intersection of a solid and a plane. So whenever you have a cross section, it is going to be some type of two-dimensional figure. For any of our polyhedrons, it will be a polygon. So yeah, anytime you're looking at a cross section of a polyhedron, it'll be a polygon or one of 2 other things, a line segment or a point. So the only ways that you can get something other than a polygon is if the plane intersects at one of the edges of the object, and then you just have a line, or if it intersects only at the vertex. So if the plane was tangent to the polyhedron, where it's only intersecting the vertex. Again, those are the only ways that you could have anything other than a polygon. Now, if you were looking at something that was not a polyhedron, so when we get into like a cone or a pyramid, sorry, not a pyramid, a cone or a cylinder or a sphere, then you can have things that aren't polygons. But again, it's still going to be either a two-dimensional figure, a line, or a point. So it'll always be one of those 3 things, a two-dimensional figure, a line, or a point. And if it's a polyhedron, the two-dimensional figures would have to be polygons. All right, so they show the intersection here of a pyramid. Now, it's kind of hard to see the actual intersection here. So if you're to try to draw these back to edges of the pyramid, you get a better idea of what the shape is that's on the bottom, because they said it's 2 square pyramids here. So this shape here, and it's not my best drawing ever, but this shape here, where the intersection is occurring, that is our cross section. So our cross section here is a square on that first image. On number 3, they do a better job of displaying it so that you can see it. So on the try it, what shape is the cross section shown? Well, this was a pentagonal pyramid because the bottom shape was a pentagon. And if you look at how the plane intersects the pyramid, the cross section is also going to be a pentagon. So again, a lot of times it'll be one of our types of polygons. So it's a pentagon. All right, on part B, what shape is the cross section of the plane? Wait, what shape is the cross section of the plane is perpendicular to the base and passes through the vertex of the pyramid? So now they're saying that we have a plane going vertical through this. So splits it right down the middle. Pretend you just cut it right in half. What would it look like if you were to open that up? Anybody want to take a guess? Yeah, so it's going to be a triangle. So on there, it will be a triangle, and it's kind of hard to demonstrate perfectly on here. And I'm not sure how this is going to work with the camera, but I'm going to see if I can demonstrate this. So give me a second. Just realized I did not bring home an expo marker. All right, well, I won't be able to demonstrate that one part today. I thought I was going to be able to demonstrate something, but if we were, let's see if I can do it with this drawing on here. Let's clear that. All right, so if I went through the point, and I'm going to try and do this at a different angle, and then connect it to the top along that edge, and then this will be going right down the middle of the other side. You can kind of see the triangle. The other thing is, if we didn't go straight through the vertex, it wouldn't be a triangle anymore. So you gotta kind of imagine, what would it look like if you didn't go straight through the top? So that question is not there, but I'm gonna go ahead and re-ask this question a different way. What is the cross section if the plane is perpendicular to the base and does not pass through the vertex? So what would happen if it did not pass through the vertex? Would it still be a triangle? So let's say I drew a line along the base that was right about here. And I wanted to bring that straight up. If I brought it straight up the triangle, it intersects the top of the triangle right about here. So then if we connected those lines, what shape do you actually see starting to form there? So keep in mind, if we were to do this, this is a three-dimensional image still, so it's kind of hard to view, but these two would be parallel down here at the bottom and the top. And then these two sides are slanting in. What type of shape is that? Yeah, trapezoid, good. So a few of you guys got it. So again, it's a little difficult for some people to imagine the cross-section part of this, but this is just trying to figure out what shape it would be if you had a two-dimensional plane intersecting a three-dimensional image. All right, let's take a look at the next part. So now this next piece is about rotation. So we have something called a solid of rotation. And what that is if you take a two-dimensional image and rotate it around an axis, what shape would it make? So on here, if you spun a triangle around an axis, what shape would it make? So on here, they kind of give you a good representation of if you were to spin this triangle, you'd be spinning it so it'd be making some type of circular image because you're spinning it around. So it actually is a cylinder. Now, there's many different shapes that can be made from doing this rotational, um, these rotational solids, but they're all going to have to be something that involve circles. So it's most likely going to be, in this case, it was a cylinder. You could also get shapes like um, this was a cone. You could also get shapes like a cylinder or a sphere or a hemisphere, but something that involves some type of circle. So now if we look at the try it down here, what three-dimensional figure is formed by rotating an equilateral triangle? And first it asks around the point BD. Well, that's essentially the same thing that we did up at the top, right? If you were to spin this around the point BD, so imagine going around BD in a circle, it's going to make that same shape that we just had up top. It's going to make it ourselves a cone. Now, if you, so, oh, that was horrible. I don't know why I just wrote with my mouse. Let me try that again. So that's a cone. The next one, what three-dimensional figure is formed by rotating around BC? Now, it's not going to be a cone. It's not going to be a cylinder. Anybody want to take a guess as to what it looks like? So it's not just going to be one of those things. So let's see if we can picture this. If I was to draw it, I'm going to first go ahead and reflect that image over that line. So something like that. So this line is spinning all the way around to over here and all the way back. Make your circular motion. So, no. So it's going to look kind of like a type of top, maybe. Two cones where the bases are connected. So it's not just one. So a 3D diamond. That's a good, yeah. Now again, it's going to be all smooth edges. It's not going to be something that has a bunch of straight cuts to it. It's going to be rounded, but I think out of the responses that you guys put in chat, I kind of like the one of a 3D diamond, but it'll basically look like two cones that are stacked on top of each other where the bases are connected. All right. All right. So this is an overview of all the different things that we talked about. So again, we have Euler's formula, we have cross sections, we have the rotation of polygons to give us rotational solids. Those are the three main topics. Most of that vocab that I did at the front, again, wasn't actually in this section, but those are words that you need to know for this entire unit. So again, please make sure you get familiar with those vocab words in the beginning so that most of the section will make sense. There's a couple did you know questions here that I wanted to go over real fast. So for the chart, again, that we're using Euler's for. So if we took these, remember our equation is going to be number of faces plus the number of vertices equals edges plus 2. So I'm going to go down the line here and fill this in. Plus, 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 plus with always equals, plus 2, plus 2, plus 2, plus 2. So as I go through this, I have 5 plus 6. That's a total of 11. 11 is not my answer here, though, because, again, this is going to be number of edges plus 2 would have to be equal to 11. So what number plus 2 would give you 11? 9. So there's 9 edges. Then we have on this one, all right, we're missing the number of vertices. Well, 8 plus some unknown number equals 18 plus 2. So 18 plus 2 is 20 minus the 8, and it is 12. Thank you, Jade. You're on top of it. Christian, you got that. Christine, you got that one. Christian, you got that one. Good. I have several other people that got it as well. You guys are doing good here. All right. 20 plus 2 would be 22. Subtract off the 12, you're left with 10. Good. And then on number 7, so 22 plus 44, that's 66. This number is not 66. Again, this is going to be 66 all together with the 2, so you got to subtract it off, which is 64. All right. Good job, you guys. All right. On number 8, what polygon is formed by the intersection of the plane and the octagon shown? So since the image, or since the plane is parallel to the bases, something to understand about this one is if you have a plane that's intersecting and it's parallel to the base, it'll always end up giving you the same shape as the base. And that's true for any prism. And it's also the same for any cylinder, right? So prisms and cylinders, it'll always be true for. And actually, it'll really also be true in cones and pyramids as well. The shape will always be retained as whatever the base shape is if the intersection is happening between the bases and it's parallel to those bases. So this will also be an octagon. All right, and then number 9. This one is similar to the last question that we had done on the previous page. This time it looks 2 cones that are sideways meeting at the base, because again, we would have that same triangle down here, but it's being spun. So if we picture it being spun, that's horrible, but again, hopefully you get the idea. I tried it with the camera earlier. I don't think the camera shows it justice if I was to spin an image. So the best I can do is draw for these. But that one, again, would give you 2 cones where the bases are connected. All right. Any questions in this section? I didn't see any hands go up. I didn't see any other questions in chat. Thank you guys for coming on. Seems like as we've been going, participation in the live sessions has been going down. So thank you, those of you that were able to join me today. Will you fill the notes? Yeah, so will I post the filled version of the notes? Yes, I will. Any other questions? All right, let me just go to this last slide then. So the last slide here is just what the assignment was. Again, the assignment, similar to what it's been, it's just part of this page. Now, some of the assignments coming up aren't just the practice part of it, but for this one, it's this entire practice, and there's one extra problem. Notice it goes to 26, not 25. So there is one other problem on the other side. All right. So we'll talk to you guys later. All right. If you don't have any other questions, have a good one.